Did you know that you are a true Speedy Gonzales? After all, you have covered no less than 6,300 kilometers in the last 10 seconds. There is a simple reason why you are not out of breath despite this rapid sprint. Strictly speaking, it is not you but the local group, together with the Milky Way and the Earth, that is racing through space at a speed of 630 kilometers per second. But how did our parent supercluster of galaxies end up on such a breakneck course? And where are we headed anyway? The first speed camera photo was taken in the 70s. In fact, it was back then that astronomers first managed to determine the speed of our galactic home using the cosmic microwave background radiation. In principle, the background radiation, which originated about 380,000 years after the birth of the cosmos and still fills the entire universe today, is considered outstanding evidence for the Big Bang theory. And yet, the conclusions about speed derived from it also left some fundamental questions unanswered. There is no question that the first precise measurement of our galaxy's speed was an important astronomical milestone, but in the same breath, it also seemed a little disconcerting. After all, at first, nobody knew exactly why the Milky Way was moving so fast. A significant part of our speed could be explained by the expansion of the universe, which in turn is described by the Hubble flow. In other words, the associated drifting apart of galaxies. Gravitational interactions between the Milky Way and its closest galactic neighbors, such as Andromeda, also contributed to the speed description. And yet, a significant piece of the puzzle still seemed to be missing. No wonder. After all, we seemed to be racing at a speed and in a direction that we couldn't fully explain. It also seemed as if our entire galaxy was being thrown off course by a gigantic, distant structure. The bottom line, however, was that not only our Milky Way had been sucked into the pool of this ominous something, no, it affected every galaxy in our corner of the cosmos. Expressed in numbers, this means nothing more than that we are dealing with a mysterious galaxy stream that extends over more than 800 million light-years. In light of this attractive force, the experts decided to christen the object responsible for it the Great Attractor. Consequently, the task at hand was to reveal the true identity of that attractor. But what brute force could be capable of drawing entire galaxies over hundreds of millions of light-years into its orbit? Well, the simple answer to this question was gravity. But to attract 100,000 galaxies over such vast distances, the Great Attractor had to be unimaginably huge and massive. The Great Attractor, true to the motto, "It's worth a try," astronomers first attempted to examine the Great Attractor with telescopes. They quickly realized that this approach would not be successful. The spiral structure of the Milky Way, which is thought to contain approximately 100 billion stars concentrated along a plane 1,000 light-years thick, put a blinker on the research view. In detail, the Great Attractor lurks in the so-called zone of avoidance, an area of the sky where structures in the optical spectrum are only weakly visible or not visible at all. As a result, the true nature of the Great Attractor initially remained a great cosmic secret. Experts could only study it indirectly by examining its gravitational influence on the surrounding galaxies. At least, however, it was possible to determine its approximate position and estimate its rough mass. We now know that it slumbers 150 to 250 million light-years from Earth in the constellation Norma and weighs an incredible 10 quadrillion solar masses. Despite this, for a long time, we knew of no structures in the universe with such an imposing mass. But advances in radio and infrared telescopes finally allowed us to see through the zone of avoidance and take a look at the areas beyond it. Sure enough, astronomers found more galaxies there, a lot of them. In this case, a lot means that the Great Attractor is nothing more than a colossal supercluster, a huge collection of galaxy clusters, among the largest known structures in the cosmos. Yet, this galactic gigantism also raises a number of profound questions, especially regarding the nature and cause of the Great Attractor. In 2016, researchers using the Australian Parkes radio telescope succeeded in shedding at least a little more light on the cosmic darkness. While the scientists were examining a certain spectral line that originates from glowing hydrogen objects beyond the Milky Way, they were able to identify 883 galaxies in the zone of avoidance, around 30% of which were previously completely unknown. In addition to individual galaxies, the region under investigation also contains 3 galaxy clusters and 2 previously unknown galaxy clusters. Given that an average galaxy contains about 100 billion stars, we can begin to imagine the unimaginable mass regions we are dealing with here. And while our Milky Way, as mentioned, is hurtling toward the Great Attractor at a speed of over 200 million kilometers per hour, a few years ago, experts made another astonishing discovery. Not only are we being drawn toward the Great Attractor, but we are also being pushed away at the same time. The center of repulsion. This finding came as a surprise to experts, to say the least. For a long time, the influence of the Great Attractor was considered the main cause of the collective movement of galaxies. But then, at a distance of 700 million light-years, astronomers discovered an even larger structure located in the constellation Centaurus, the Shapley supercluster. It is the largest known collection of galaxies of any kind, and the powerful gravitational forces at work here even ensure that the galaxies belonging to it do not move further apart, despite the expansion of the universe. Yet, even the existence of this cosmic superstructure was not enough to fully explain the motion of the Milky Way and its neighboring galaxies. This made the discovery by Yehuda Hoffman's research team at the Hebrew University of Jerusalem all the more important. Their study revealed yet another force influencing our home galaxy on its breakneck journey through space. The researchers reconstructed the movement of galaxies in our supercluster using various telescope data. Based on this, they created a flow field of our cosmic environment, mapping the lines of motion and velocities of its structures. Surprisingly, this model showed that the galaxy's lines of motion were not only converging on the Shapley supercluster, but also on a region in the opposite direction, where noticeable concentration of motion was observed. However, this concentration appeared to have a repelling effect rather than an attractive one. This low-density region, called the Dipole repeller, thus pushes the Milky Way away to a considerable extent. The experts' investigation showed that the influence of the Dipole repeller is almost as great as that of the Great Attractor. While this cosmic shove is characterized by significantly fewer galaxies and clusters than other areas of space, this was the first time researchers had ever identified such a source of repulsion in space. The impossible voids. Just how much remains to be learned about the overarching structure of the cosmos is demonstrated by a surprising discovery made a few months ago. According to this, our Milky Way might not actually belong to the Laniakea supercluster after all, but instead directly to the significantly larger Shapley supercluster. Meanwhile, the existence of voids, massive empty regions in space, poses another mystery. The standard model suggests matter should be evenly distributed throughout space, but voids suggest otherwise. If our Milky Way is inside one of these low matter bubbles, it could explain the Hubble tension, the fact that the universe is expanding faster than it theoretically should. As for our final destination, ironically, despite our rapid speed, we will never reach the Great Attractor. The accelerating expansion of the universe will ensure that the distance between us and the Great Attractor actually increases over time. While our local group remains bound by gravity, the rest of the cosmos will drift away into the darkness of space.